There is.
There is similarity. Okay. Do you know them or are you just guessing? So,
No.
yeah. Suyog Bhattrai. Suyog Bhattrai. Binary trees and binary search tree. What do you think is the distinction or similarity between them? Are they the same? Just answer this. Are they the same or are they different? What do you think? Just give a random answer if you don't know.
Maybe same. I don't know.
Maybe same. Same or different?
Same.
Okay, same. All right. We'll get to that. We'll get to that. Just let's get the definition of a binary tree clear, and then I think you can connect the dots because we've already talked about binary search tree. We also did a visualization exercise on the class. A binary tree consists of a header. Okay, think of it as a linked list first. A linked list contains a header. It contains nodes, which contains element and address to the other nodes. And the header contains the address to the first node or the last node, depending on the nature or if depending on the type of a linked list. It might be a single linked list or a double linked list. Similar to that, a binary search tree consists of a header, all right, plus a number of nodes. There are different nodes connected by links in a hierarchical data structure. So hierarchical data structure. If there's an organization in the organization's algorithm, sorry, not algorithm. In the organization's organogram, you can see that the C-suite employees, CEO, CFO, CTO, all of them are on the top of the hierarchy, right? And then comes the regional managers or the vice presidents and all of them maybe, and then it might be followed by employees. It might be followed by supervisors and managers, and then it might be followed by employees, depending on the organization, right? And so that is a hierarchy of positions in an organization. Similarly, in a binary tree, you have hierarchy of nodes which are connected by links. So a binary tree is a hierarchical data structure which is connected by links, where the nodes are connected by links. Okay, each node contains an element. This is evidential. This is clear. If this rectangular box is called as a node, we can see see an element, an alphabet inside. In this case, which is the element, it might be a value or an object, plus links to at most two other nodes. At most two other nodes. दुईटा भन्दा बढी लिङ्क हुँदैन, 0 वटा हुन पनि सक्छ, एउटा नि हुन सक्छ भनिएको. The header contains a link to a node designated as the root node. Root node is the first is the node which the header has the address to. A node with no child node, a node with no child node, or a node having both of the links as null. It's a leaf node, except the root node. If a node doesn't have links to two links, on the of either of the left or right side, दुईटै छैन भने it's called as a leaf node. So header, leaf node, and root node are clear. A leaf node is one that has no children, i.e. both its links are null. Every node except the root node, if is the right or left or right child of exactly one other, its parent. So B is the node containing the element B, the node containing the element C are the parent of the node containing the element D, and that of E and F respectively. So parent node is clear. The size of a binary tree is the number of nodes. So number of nodes here are 3 and 4, 7 nodes here. So the length of this binary tree is 7. An empty binary tree has size 0. Its header is null. This, I guess, I don't have to explain the part where header is null. We've already talked about it in a linked list. Each node has both a left subtree or yes. Is there a question? Interesting choice of picture. Cyrus, your mic is on, not on mute. Okay, okay. I guess he's talking somewhere. Rahul, please inform it to him. I put him on mute because it's none of our concern what he speaks. Okay, Rahul, do let him know.
Okay, sir.
And this is not acceptable, really. Please let him know this as well.
So you have right to remove the student from the class.
Okay, yes, thank you. Thank you for reminding me, and I'll do that. Exactly. Yes, good thing he's leaving on his own. Ask him to write to me, not on message, but on email. Okay. Each node has both a left subtree and a right subtree, either of which may be empty. The node's left subtree consists of nodes left child together. Left subtree consists of a node's left child together, all of it. So A's left subtree consists of the node B, which is a parent node to the leaf node, that is D. B's left subtree is empty because there's no leaf extending from B on the left. But the subtree, the right subtree of B consists of the node which contains the element D. Similarly, these images or these colors, or if you may, this green color, it says that it's a subtree. It's C's left subtree. Similarly with these, so subtree is also done. So it's a kind of a recursion, right? Tree ma subtree also, subtree is also a kind of a tree in itself. So each subtree is itself a binary tree. This gives rise to an equivalent recursive definition. A binary tree is either empty, which means that you don't have links to the other nodes. I mean, if by saying that you don't have links, I mean that the links are null. Okay, the links of the left, on the left and on the right here, are null. Non-empty, in which case it has a root node containing an element, a link to the left subtree, and a link to a right subtree, or you may just call it as either then and. The word or is also sufficient here. Okay. एउटा मात्रै subtree भए पनि either left or right, it works fine. So let's get back to this one. Let's make some observations here. For any node n in a tree, there is exactly one sequence of links between the root node and n. So let's select this node E over here. How many links are there from the root node? I'll ask one of you, which will be Vikita Sharma. Vikita Sharma, how
Yes,
many
sir.
how many links is this node with element E from the root node? Root node बाट कतिवटा लिंक पछि चाहिँ root यो नोड आउँछ जसको एलिमेन्ट E छ. How many links after the root node?
Sir,
दुईवटा, right? So this A to C and C to E, right? These pointers, if you count these arrows, this one unidirectional arrows, you can see that there is exactly two sequence of links between the root node and the node containing the element E. The depth of node n is the number of the links between the root node and n. So it's called as the depth. So Bikita, what is the depth of the root of the node containing the element E? What is its depth? This level. जुन E छ यसको depth कति भयो त? अघि कतिवटा Duita, right? So it's 2. The depth is equal to 2 here because there is this 2 sequence of address or this 2 sequence of pointers, exactly 2 sequence of links between the root node and the node that contains the element E. So that is clear. Depth भनेको के हो भन्ने कुरा हामी सबैलाई थाहा भयो. So this begs the question, root को depth चाहिँ कति हो नि सर भन्नुहुन्छ. So root त आफ्नै rootमै छ, right? There is root to root, there is no difference. So it's called as 0. And conventionally, the depth of header is considered as -1. Conventionally, okay, it's in convention that an empty tree has depth -1. The header matray भयो. If it's null, the empty has depth -1. Okay, so you could use this while you code, right? I mean, like code. You can, let's say there is this. Yes, Rahul.
So for G, how many links? Is that 3 or 4?
For G, it's 1
I guess
from
3.
root node. Root node बड़ा है. भनेपछि कतिवटा छ? A to C, C to F, and F to G. So 3.
Okay, so we don't need to count E.
No, you don't need to count E. E doesn't come in its path, right? G सम्म आउनको लागि root देखि G सम्मको आउनको लागि एउटा distinct link हुन्छ, right? Unique to itself, right? So A to C आयो, C to F, and F to G, which is 3 links from the root node, which is why the level of G is 3. Note that D, E, and F, all of them are at level 2. B and C are at level 1, the root node 0. And if it were an empty binary tree, it would be -1, and -1 is a convention. Okay, moving forward. So let's say, as I was talking about this, what you can do is that let's say there's a problem that you need to analyze binary trees, whether you need to share the or you need to find out the, let's say, the maximum depth of it, right? And if the header is null, you could return -1. तपाईँले return 0 गर्नुभएको थियो int main मा. If you remember correctly, program को flow main सम्म आयो, यो लाइन सम्म program आइरहेको छ भनेर, program को flow मा कुनै interruption छैन भने त्यसले जनाउँथ्यो भने, if you might use this idea of depth -1, depth is equal to -1 if you find that the header is empty. Okay. So is there any chat messages here? No. So I'll check the others later. It has illustrated and it has labeled. Note that it has labeled these trees, these binary trees, as balanced and ill-balanced. So what qualifies as a balanced and ill-balanced will be our topic of discussion for this slide and the next. But note that this depth 0, depth 1, and depth 2, I guess you are all pretty accustomed to how a depth is calculated. Root node भन्दा कति छ भनेर. There were actually some other nodes here. I removed it. Let me just add them. But I removed it for E and then D. So let's see what qualifies as a balanced and an ill-balanced tree. It says it's very ill-balanced, right? The trails on the right are just long. Balanced binary trees. A binary tree of depth D is balanced. Okay, what qualifies as a balanced? If all nodes at depth 0, 1 have 2 children. Okay, depth -2 sum. Depth, maximum depth 2 sum, right? 0 देखि 2 - 2, yes. Please go on. Yes, anyone? Someone was speaking. Okay, I guess that was a mistake or something, but let's continue. A binary tree of depth D is balanced if all nodes at depth 0, 1 up to D - 2 have 2 children. if all nodes at depth 0, 1 up to d minus 2. So d, if there is this maximum depth of 2, then balance के हुन्छ भने balance के हुन्छ भने d minus 2 have 2 children. So d minus 2 यो जुन root node छ, if all nodes at depth 0, 1, 2, d minus 2 means 0 to 0 have 2 children भनेर भनेको छ. यसमा चाहिँ depth 2 सम्म भएको भने चाहिँ depth 2 सम्म भयो भने 0 जुन यो फर्स्ट रूट छ यसको चाहिँ दुईटा चिल्ड्रेन छ भनेर भनिएको छ. Nodes at depth d minus 1 may have 2, 1 or no children. Nodes at d minus 1 means this is the node d 2 minus 1 भनेको have either 0, 1 or 2. Okay, we'll see how it doesn't qualify for an unbalanced tree and how a binary tree of depth 0 or 1 is always balanced. So balanced definition is, it says it here, and then it says that depth 0 or 1 binary tree is always balanced. Let's see if you d, e, f, if it will not exist, it didn't exist. This is why I removed it in the previous class. Depth 2 मा कुनै पनि आइटम छैन, depth 0 र 1 मात्रै छ भने it's always balanced भनेर भनिएको छ. Because nodes at any depth, so leaf node को चाहिँ अथवा त्यो root node बाहेक root node को 2, 1 or no children is sufficient. So a balanced binary tree, your balanced binary tree arrow, I'll just control Z here, undo this. If this is a balanced tree, minimum कतिवटा आइटम हुनु पर्दो रहेछ र maximum कतिवटा आइटम हुन सक्छ भन्ने कुरा चाहिँ can we just make an assumption? If it is full, then it would be like 8. 1, 2, 3, 4, 5, 6, sorry, 7 items, right? 7 items, 7 nodes in a total. It would contain a 7 nodes in total. If it were, the minimum would be, how much would the minimum be? If it's of depth 2, the minimum would be, I guess, 3. So let's see, 3 or 4. Let's see. A balanced binary tree of depth d has at least 2 power d nodes, and at most 2 power d plus 1 minus 1 conversively. So this is the next part. So let's take the most case here. At most case here. So the depth of this balanced tree is 2. D plus 2 plus 1 would give us a 3. 2 power 3 would be 8 and minus 1 would be 7. Just as we talked about, at most 7 element on SESMA. And at least 2 power d. So d is 2. 2 power 2 will give us a 4. 2 power 2 will give us a 4. An ill-balanced binary tree of depth d could have as few as d plus 1 nodes. As few as d plus 1 node. So it has depth 5 and it has 6 element. As few as, you can see that. It has depth 3. It has as few as 4 or some on this one node 0. Maximum it hasn't said, but minimum say d plus 1 some more. It has as few as d plus 1 nodes. So
हेलो सर.
yes, Anus.
सर हामीले त्यो हेडरलाई चाहिँ नोट काउन्ट गरिदैन. ओके सर.
Okay. An ill-balanced binary tree of depth d could यो भनिएको छ, यो जुन conversely भनेर भनिएको छ, it's just the opposite of that. Depth of balanced binary tree of size n, यदि 8 वटा नोड छ भने floor value of log यो 3 हुन्थ्यो यसको depth, right? So let's say we have 8. We have a size of a tree which has 8, which has 8 nodes. What would be the depth then? Which has 8 nodes. What would be the depth then? The depth would be 3 because log 8 to the base 2 will give us a 3. The floor value is still a 3 because it's a whole number. Similarly, the maximum depth of ill-balanced binary search tree of size n is equal to n minus 1 भनेर भनिएको छ. Node हामीसँग यदि 8 वटा, if there were 6 nodes, then the maximum depth could be 5, as in this one here. Okay, so depth you can also, for your sake of understanding, level भन्दा पनि हुन्छ. Level 0, level 1, level 2, level 3, level 4, level 5. Any generalization which makes it easier for you to understand it, but to use the jargons, depth may use गर्नुपर्छ. Okay, for your understanding you can assume it anything, but while you write answers or while you do something binary search tree explain, when you are doing some explaining of binary tree or binary search tree, use the word depth. Done. Okay. Coming to the question we put forward on the start of this presentation about how about is a binary tree different with a binary search tree. We saw that a binary tree has left and right child nodes. It has root nodes. And we also, when we visualized binary search tree, we saw that a binary search tree also has these. But then we can, so far we can, come to this observation that binary tree मा चाहिँ सरले लेफ्ट र राइट सानो र ठुलो हुन्छ भनेर भन्नुभएको चाहिँ थिएन. सानो ठुलो कता राख्ने भन्ने क्वेसन आएको हुन सक्छ. त्यो आएको हुन सक्छ भने this thing with the left node and the right node being smaller or greater is of this total deal is of a binary search tree. So a binary search tree is also a binary tree, but then a binary tree might not essentially be a binary search tree, because a binary search tree has the same properties as that of a binary tree. But in addition to that, for any node in the binary tree, for any node in a binary tree, mind the cursor in the screen being shared. For any node in a binary tree, the left node contains the element that are smaller than the element of the current node, and the right one, you know the deal, right? If its left subtree, if non-empty, of course, contains only element less than ELEM of that node. Its right subtree contains only elements greater than ELEM. You already know this, so I'm not going to illustrate this again. We've already talked about binary search tree. So an equivalent recursive definition is also possible. It says a binary search tree is either empty or it is non-empty, in which it has three cases, or it has three cases: a root node containing an element, a link to the left subtree. If it is there, it's less than ELEM element of the root node. In our case, if it's of only of a depth 1, a link to a right subtree in which all elements are greater than ELEM. So implementation, it has first defined the element and the links. It says that while we initialize a node, we can see that every element assigns a, and while we initialize a node, the left and the right links are set to null. So that was about initialization of BST. Please make note of that. पहिला नोड नै डिफाइन गर्नुपर्ने रहेछ, त्यसपछि बल्ल ट्री डिफाइन हुन्छ. ट्री डिफाइन गर्दाखेरि ट्रीको रुट भ्यालुमा नल पास गरेको के छ भने, you pass null here, comparable ELEM will become null. So the element, so entirely null हुन्छ सुरुमा. The node is entirely null. Element and the left and the right subtree, right link or address are set to null. These are then followed by the methods. Also note that yeah, protected भनेर लेखिएको छ. Okay, it means outside of the scope, not accessible directly. Not accessible directly. You need to make use of the operations as in the ADT we saw. ADT को chapter में हमले देखेको थियौं. And it helps us. It keeps it intact. Gives certain level of abstraction to it. BST. Search for a given target value in a BST. I don't think that we need to go into what a BST is or how it's done, but let's directly go to the algorithm then. I will require one of you to volunteer with me. It will be Samarpan. Samarpan Kafle.
Ajay sir.
Okay, please be with me. Aita.
Okay.
Slides so current. Okay. What the target here PIG search गर्नुपर्ने छ. Okay, whether the node, whether this binary search contains PIG or not. So target like के राखिएको छ. What is the value of target? PIG, right? Pig. Step 1 मा के भएको छ? Step 1 मा के भएको छ? They have created something called as square, which is the address to the root node. Okay, same address points to the node contain the root node or the node containing the item line, which is the start. Right? Start. So lexicographically, P अगाडि आउँछ कि L अगाडि आउँछ? Alphabet order ma L comes L अगाडि आउँछ, right? So what? So now if we go through this, if what it does is that set boy value step 2.1 मा के भइराको छ? If current is null, terminate with answer none. You execute हुन्छ कि हुँदैन? If is current null, Samarpan, current null छ कि छैन? CURR, is it null?
छैन sir.
छैन. So step 2.1 लिँदैन है. 2.2 मा जान्छ त्यस पछाडि. त्यो comparison fail भइसके पछाडि. Is it equal to the current element? जुन target को value? Target को value र CURR जुनले point गरेको जुन node छ, is it equal?
No, छैन.
No. It then comes to which step? 2.2 पछि कुनमा आउँछ?
2.3.
2.3 मा के भइराको छ?
If the target.
So is it less than the current element? P is less than the current element. Lexicographically, P अघि आउँछ कि पछि आउँछ? Is it less or is it more?
पछि आउँछ.
पछि. So it's more, right?
Yes.
The target is more than the current, which means 2.4 मा आएर 2.4 मा आएर के गर्छ भने current change भएको छ. CURR is now set to पहिले त्यो लाइन को राइट साइडमा सेट भएको छ. यतिसम्म क्लियर छ?
Yes sir.
Okay, so next step मा के हुन्छ? You can, it's pretty obvious. Step 2.1 बाट आएर आउँछ. 2.1 हुँदैन, 2.2 हुँदैन, 2.3 मा आएपछि it finds that it's less so that अब current change भएर PIG मा आउँछ. अनि फेरि कम्पेयर गर्दाखेरि चाहिँ के थाहा लाग्छ भने current र PIG, current र CURR र target same छ. It returns अनि के भयो भने found हुन्छ root node अनि address CURR को we have the address. So in this way binary search success is done. Unsuccessful case मा पनि त्यही नै हो. कर चाहिँ null हुन्छ पछिसम्म, last मा null हुन्छ अनि it means that it has not been found. BST को search मा हामी जाँदैनौँ because we've already talked about binary search tree. We've already done the visualization. Coming on to this, it's important. ध्यान दिएर सुनौ, ध्यान दिएर हेरौ. Let the BST size be n भनेर भन्ने. So that means the number of node that the BST contains is n. If BST has depth d, the number of comparison is at most d plus 1 भनेर भनिएको छ. Okay, d plus 1 भन्छ अगाडि हेरौ. If the balanced search tree is well balanced, if the binary search tree is well balanced, its depth is the floor value of log n to the base 2. Log n to the base 2. Maximum number of comparisons is given by the log n to the base 2, its floor value added to 1, and the base case time complexity balanced by when it's the base case. The base case time complexity is given by is of a logarithmic order, while in the case of a binary search tree which is ill balanced, its depth is at most n minus 1 baniega sa. Okay, so maximum number of comparisons will be equal to n, which means the best worst case time complexity is of a linear order. When I say linear of a linear order, of a logarithmic order, of a linear logarithmic order, of a quadratic order, of a cubic order, of a exponential order, I hope that makes sense to you. Okay, time complexity tapaharule big O, small o, theta notations. I had also uploaded an article on that. अलिअलि थियो यो बुझ्नु भएकै होला. This is the most important of all. Algorithm to जान्नु परि नै हाल्यो, that's okay, but time complexity you must be able to analyze it, compare it. Basically अहिलेसम्मको हामीले day 1 देखि हामीले हेर्दै आएको छौँ. Log n seems the best, and it is the best because remember the graph, best case time complexity. So if you use a binary search tree, if you make sure that it's balanced, then the time complexity will be of a logarithmic order. Implementation part. So I told you yesterday, dev cpp, dev C++ in Windows, get it ready. If it's Linux, use what makes you feel easy. If it's Mac, use what makes you feel easy. If it's this dev cpp, it will be better because everyone will be using that. And कुनै पनि problem भयो for Windows, then contact Rahul. Okay, Rahul, please help them with dev cpp if they have a problem. And if it's Linux or Mac, please contact me. I use Linux, I'll figure it out for you. Okay, so get your compilers ready. Just code some hello program or anything you like. BST insertion, what's the time? 53. Okay, let's take it then, because we already started 10 minutes late. Rahul, next class बाट अलिकति सरलाई अलिकति रिमाइन्ड चाहिँ गरिदिरहनु होला. I'm sure you did it, but do let him know. I cannot take my 10 minutes time. पछि गएर मैले धेरै कभर गर्नुपर्छ एकैचोटिमा, अनि I will have to rush. है?
Yes, sir. Okay, sir.
भनिरहनु होला उहाँलाई. Okay, so let's check the participation. Again, because if you are participative, it will be more motivational for me. Prince Bohra. Yanji Lama.
Yes, sir.
Okay. Janice Karki.
Yes, sir.
Anus already spoke. Okay. Ades Paudel. He's here, I know.
Yes, sir.
Yes. Okay. So who was the one to not speak? It was Prince, right? If there's a problem, Prince, leave us a message. Or if he doesn't respond by the end of the class, Rahul, you know what to do. Okay. The idea here is to insert a new element into a binary search tree. Proceed as if searching for that element. If the element is not already present, the search will lead to a null link. Replace that null link by a link to a leaf node containing the new element. Okay, whatever that means, we'll see from current slide. Rahul, next class at 10:30, right? Okay, we'll complete this.
Yes, sir.
If I have to take few more minutes, we'll take it. BST insertion in an empty binary search tree. So the basic idea is, well, let's search गर्नु पर्यो रे. Okay, you need to first search. If the element is not already present or not, the search will lead to a null link. यदि छैन भने null link मा लान्छ. And then replace that null link by a link to a leaf node containing the new element. it has some values, set some values, parent as null, current CURR, which I'll refer to as current, as the BST is root. It repeats these steps 2.1 through 2.3 and 2.4. In the case that the empty is the in the case that a binary search tree is empty, we know that root ma ke huncha, Rahul? Can you guess? If the binary search tree is empty, root ma kun address huncha? It's null. Step 1, parent will be set to null. CURR will be set to the root node, which is also null. If the current is null, replace the null link from which current was taken by a link to a newly created leaf node with element goat and terminate सकिन्छ. Null हुन्छ भने सक्यो. Comes to a non-empty binary search tree, set parent to null, and then parent to null and CURR to the BST's root, which is CURR is equal to root भनेर हामीले पहिला छ. So CURR will be the address or the link to the node, to the root node, that is lion LION, which has the element LION. Step 2.1 will not be true because we've already seen that CURR is not null. If element is equal to current element, terminate भनेर भनिएको छ. If ELEM is equal to current element, okay, हामीले insert गरिरहेको के छ? GOT छ. If it is equal to the current element, so that is LION. Depends है, बाइनरी सर्च ट्रीको एक्जिक्युसनमा कसैले चाहिँ सेम भयो भने लेफ्टमा पनि हाल्दिन्छ. ओके, सेम भयो भने लेफ्टमा राख्दिन्छ some binary search tree. But this one here, it says it will terminate if ELEM is equal to C. Find भयो भेटियो भने चाहिँ terminate गरिदियो भने छ. नभयो भने चाहिँ 2.3 मा के गर्नु भनेछ भने if ELEM is less than current element, is it less? No, it's not less. No, yes, it is less. G comes before. So if ELEM is so, yes, it is less. Set parent to CURR भनेर भनिएको छ. Okay, set parent to CURR भनेर भनिएको छ. So now the parent is LION and set current to current's left child भनेर भनिएको छ. Okay, CURR पहिले लाइन थियो, त्यसको लेफ्ट साइड अब फक्स भएको छ. Okay, 2.3. If current is null, replace the null link from this. If current is null, replace the null link from which current was taken by a link to a newly created node. Empty को केसमा जे भएको थियो त्यही 2.1 को केसमा एक्जिक्युट भएको छ. Counting comparisons, if we count the comparisons, the number of comparisons is same as for BST search नै गरेको पहिला. If it is well balanced, best case is of order of a logarithmic order. If it is of a ill balanced, if the binary search tree is ill balanced, can you guess what happens in this case? Janice, if the binary search tree is ill balanced, can you make a guess of what happens while we insert it in a binary search tree?
What? So you mean max on comparison?
Yes, maximum or yes.
N minus 1.
Time complexity कति होला त?
That ON I think.
ON भन्दा पनि ON लेख्दाखेरि चाहिँ O parenthesis open N parenthesis close लेख्नुहुन्छ भन्दाखेरि चाहिँ of order N भन्नुपर्छ है.
Yes sir.
Okay, because we are DSA students, we've come so far. We will use the word of order
N.
Linear, logarithmic, quadratic, cubic, exponential, and so on. So maximum number of comparisons here. भेट्दै भेटेन भने के हुन्छ भने जतिवटा नोड छ त्यतिवटा सर्च गर्नु पर्यो, which is equal to n. Ill balanced. So the worst time complexity is of order, is of a linear order. Yes, is of a linear order. अनि तपाईले सम्झिनु छ होला हामीले टाइम कम्प्लेक्सिटीहरु बनाउने बेलामा 3 वटा स्टेप्स थियो नि. Do you remember the 3 steps? कुनै पनि सानो इन्क्रिमेन्ट अथवा कुनै पनि कन्स्टेन्ट इन्क्रिमेन्टलाई, सपोज यसको केस थियो भने कुनै पनि सानो इन्क्रिमेन्टलाई के गरिन्छ, रिमुभ गरिन्छ भनेर भनेको थियो. मेन टर्म जुन छ त्यही लिइन्छ भनेर भनेको थियो, राइट? त्यसपछि यो फ्लोर पनि त्यति धेरै होइन, 2 देखि 2.3 को बीचमा आउने सबैलाई 2 भन्न मिल्छ. राइट सो त्यो पनि हटाउँछ अनि logarithmic order जुन छ यो 2 हुन सक्छ of order it can be of order 2 3 4 5 and so on हो it can be of many orders so त्यो पनि एउटा constant जस्तै doesn't really matter so लास्टमा के मात्र लिने हो भने जुन मेन जुन हाम्रो यो लिनियर logarithmic त्यो आउँछ त्यो चाहिँ लिने हो 2 power n हुन्थ्यो भने we would have put it 2 power n and that would be a nightmare in case of a DSA. Okay, BST insertion is done. This implementation will take care of in C language. Okay, BST in practice. We'll resume it from here. Rahul, please note the slide number 1029, slide 29, and we will start from 29. Okay, we'll try to finish this BST tomorrow. भोलि हामी यो सकाउन ट्राई गर्छौँ सो of course अघि मैले भनिसकेँ राहुललाई please try to all attend by 9:03 सम्म सबैजनाले जोइन गर्नु होला 2 minutes time given there भोलि म 9:03 मै स्टार्ट गर्नेछु we'll finish binary search tree tomorrow we'll try to finish it no worries तपाईहरुले बुझ्नु भएन भने I can repeat it for next week as well because that is my primary concern so that's all from today's class I'm going to stop the recording